What if I told you the most successful theory in science is also the one we don't truly understand? It predicts the behavior of atoms, powers our technology, and shapes modern physics. Yet even the greatest minds admit something unsettling. We can calculate it, but we can't fully grasp it. Imagine a world where a particle can be in two places at once, where simply looking at something changes what it is, where certainty disappears, replaced by probabilities. This is not science fiction. This is the microscopic reality that governs everything around us, including you. So why does this theory feel so incomprehensible? Because our brains are wired for a world of solid objects, clear positions, and predictable outcomes. But at the smallest scales, nature refuses to follow those rules. Instead, it speaks a language of waves, uncertainties, and strange connections that stretch across space. And here lies the warning. Just because we can write the equation doesn't mean we truly understand what they mean. The theory works with astonishing precision. It predicts outcomes with accuracy that no other scientific framework can match. Every experiment confirms it. Every device built upon it functions flawlessly. But when we try to explain why it works, things become unclear. Take superposition, the idea that something can exist in multiple states at once. Mathematically, it's clean and precise. Conceptually, it's almost impossible to visualize. Or consider measurement. Before observation, a system exists in probabilities. After observation, it chooses a definite state. But what exactly counts as an observation? And why should it matter? These are not small gaps in knowledge. They strike at the core of what reality is. The deeper we go, the more it feels like nature is telling us, you can predict me, but you may never fully picture me. And that is the essence of the warning. It reminds us to stay humble, to recognize that understanding is not just about equations or results, but about meaning. And sometimes meaning remains just out of reach. Quantum mechanics challenges everyday intuition because it describes a level of reality that operates completely differently from the world we are used to experiencing. From the moment we are born, our brains learn patterns based on what we can see, touch, and predict. Objects fall downward, not upward. A ball thrown in the air follows a smooth path. A car cannot be in two places at once. These patterns form the foundation of what we call common sense. However, quantum mechanics reveals that this common sense is not a universal truth. It is only a limited framework shaped by our everyday environment. At extremely small scales, such as atoms and subatomic particles, nature behaves in ways that seem almost contradictory to everything we have learned. Instead of having a definite position or path, a particle is described by a range of possibilities. It does not simply exist in one state, but in a combination of states until it is measured. This is not just a limitation of our knowledge. It is how reality itself appears to function at that level. The idea that something can exist in multiple states at once directly conflicts with the clear single-outcome experiences we are familiar with. One of the biggest reasons this feels so difficult to accept is that human intuition evolved for survival in a macroscopic world. Our ancestors did not need to understand atoms behaving like waves or probabilities in order to hunt, build shelter, or avoid danger. As a result, our thinking is deeply rooted in certainty and definite outcomes. When we encounter a framework where certainty is replaced by probability, it creates a sense of discomfort and confusion. It feels as though the rules of logic are breaking down, even though they are simply being replaced by a different set of rules. Another challenge is that quantum behavior cannot be directly observed in the same way as everyday objects. We cannot see a particle being in multiple states at once with our eyes. Instead, we rely on mathematical descriptions and experimental results. These results consistently confirm the predictions of quantum theory, yet the underlying picture remains abstract. This gap between mathematical accuracy and conceptual clarity makes it hard for the mind to form a clear image of what is happening. We are used to understanding things by visualizing them, but quantum mechanics resists visualization. Furthermore, language itself becomes a barrier. The words we use are designed to describe familiar experiences. Terms like position, movement, and state carry assumptions rooted in classical thinking. When applied to quantum systems, these words can become misleading or insufficient. We try to describe something fundamentally unfamiliar using tools that were never meant for it. This creates confusion, not because the theory is inconsistent, but because our way of expressing ideas is limited. The deeper implication is that intuition is not a reliable guide to truth in all domains. In everyday life, intuition works extremely well because it matches the scale at which we live. But when we step outside that scale, especially into the microscopic world, intuition begins to fail. Quantum mechanics forces us to confront this limitation. It shows that reality is not obligated to align with human expectations or mental models. This does not mean that understanding is impossible, but it does mean that understanding must be redefined. Instead of relying on mental pictures or familiar analogies, we must accept abstract reasoning and mathematical relationships as valid forms of comprehension. In this sense, quantum mechanics does not just challenge physics, it challenges the way we think about knowledge itself. Reality at the microscopic scale behaves probabilistically rather than deterministically, which marks a profound shift from how we usually understand the world. In everyday life, events appear to follow clear and predictable patterns. If you throw a stone with a certain force and angle, you can calculate exactly where it will land. If you know the speed and direction of a moving car, you can determine its future position. This kind of predictability is called determinism, where the present completely determines the future. It creates a sense of certainty and control, reinforcing the idea that if we know enough details, we can predict everything with precision. At the quantum level, this certainty disappears. Instead of definite outcomes, nature provides probabilities. When dealing with particles like electrons or photons, it is no longer possible to say exactly where a particle is or where it will be at a specific moment. Instead, we can only describe the likelihood of finding it in a particular place. This is not due to faulty measurement tools or incomplete knowledge, but a fundamental feature of how nature operates at that scale. Even with perfect instruments and complete information, the outcome of an individual event cannot be predicted with absolute certainty. This probabilistic nature is deeply embedded in the mathematical framework used to describe microscopic systems. Rather than tracking precise positions and velocities, the theory uses probability distributions. These distributions represent all the possible outcomes and their likelihoods. When a measurement is made, one of these possibilities becomes actual, but before that moment, there is no single definite state. The system exists in a spread of potential outcomes, each with its own probability. This idea challenges the classical belief that randomness is simply a result of ignorance. In everyday situations, randomness often means we lack enough information. For example, when flipping a coin, we call the result random because we do not track every tiny force acting on it. In principle, if we had complete knowledge, we could predict the outcome. However, at the quantum level, randomness is not just practical, but intrinsic. Even with complete knowledge of the system, only probabilities can be assigned. This introduces a new kind of uncertainty that cannot be eliminated. One of the most striking consequences of this probabilistic behavior is that repeated experiments under identical conditions can produce different outcomes. If you perform the same measurement on identical particles prepared in the same way, the results will vary. However, when these experiments are repeated many times, a stable pattern emerges. The probabilities predicted by the theory match the statistical distribution of results with remarkable accuracy. This consistency and randomness is what makes the theory reliable, even though individual events remain unpredictable. This shift from certainty to probability forces a rethinking of what it means to understand something. In a deterministic framework, understanding often means being able to predict exact outcomes. In a probabilistic framework, understanding means knowing the range of possible outcomes and their likelihoods. It is a different kind of knowledge, one that embraces uncertainty rather than trying to eliminate it. The concept also raises deeper philosophical questions about the nature of reality. If outcomes are not determined until they occur, what does that say about the state of the world before observation? Does reality exist in a definite form, or is it fundamentally a collection of possibilities? These questions blur the line between physics and philosophy, showing that the implications go beyond calculations and experiments. The probabilistic nature of microscopic reality does not make the theory weaker. In fact, it is one of its greatest strengths. It allows for incredibly accurate predictions in situations where classical approaches fail completely. Yet at the same time, it challenges deeply held assumptions about certainty, causality, and the nature of knowledge itself. The idea that observation affects outcomes, often referred to as the measurement problem, is one of the most puzzling aspects of quantum theory because it challenges the assumption that the act of observing simply reveals what is already there. In everyday experience, looking at something does not change its fundamental state. A chair remains in the same position whether someone observes it or not. Observation is passive. It gathers information without altering reality in any meaningful way. This deeply ingrained belief begins to break down when we examine systems at the microscopic level. In quantum systems, the act of measurement does not just uncover a pre-existing property, it plays a role in determining the outcome itself. Before a measurement is made, a system is described as a combination of all possible states it could be in. This is often referred to as a superposition, where multiple possibilities coexist simultaneously. However, when a measurement occurs, this range of possibilities appears to reduce to a single definite outcome. The transition from many possibilities to one actual result is what makes observation so unusual and difficult to interpret. This raises an immediate and unsettling question: what exactly counts as a measurement? Is it the interaction with a physical device, such as a detector or sensor, or does it require a conscious observer? Different interpretations attempt to answer this in different ways, but there is no universally accepted explanation. Some views suggest that any interaction with the environment is enough to select an outcome, while others argue that the role of information or awareness might be more fundamental. The lack of agreement highlights how deeply this issue challenges conventional thinking. Another layer of complexity comes from the fact that measurement inevitably involves interaction. To observe a particle, we must interact with it in some way, often by sending light or another particle toward it. At the quantum scale, even the smallest interaction can significantly disturb the system. This makes it impossible to separate the act of observation from its effect. The system being measured and the measuring device become linked, forming a combined system that evolves together. As a result, the outcome cannot be viewed as independent of the measurement process. The mathematical framework describes this change as a sudden shift from a spread of probabilities to a single outcome, often called the collapse of the wave function. Before measurement, the system is represented by a mathematical object encoding all possible outcomes and their probabilities. After measurement, only one of those possibilities remains. What causes this transition is not clearly defined within the standard formalism, which is why it is considered a problem rather than a solved feature. The equations can predict probabilities with incredible precision, but they do not fully explain how or why one specific outcome is realized. This situation challenges the classical idea that physical properties exist independently of observation. In quantum systems, properties like position or momentum do not always have definite values until they are measured. Instead, they are described in terms of potential outcomes. This suggests that reality at this level is not a collection of fixed attributes, but something more fluid and dependent on interactions. It introduces a level of ambiguity that is absent in classical descriptions of the world. The implications extend beyond physics into deeper questions about the nature of reality and knowledge. If observation plays a role in shaping outcomes, it becomes difficult to maintain a clear boundary between the observer and the observed. The traditional view of a detached, objective observer is no longer sufficient. Instead, the observer becomes part of the system being studied, at least in terms of influence. This does not necessarily mean that human consciousness controls reality, but it does indicate that the process of gaining information is not as straightforward as it once seemed. The measurement problem highlights a gap between the predictive success of the theory and our conceptual understanding of it. It shows that even when a framework works perfectly in practice, it can still leave fundamental questions unanswered. The idea that observation affects outcomes forces a reconsideration of what it means to observe, to measure, and even to define reality itself. The statement that mathematical models work perfectly yet remain hard to interpret conceptually captures one of the deepest tensions in quantum theory. On one hand, the mathematical framework delivers predictions with extraordinary accuracy. It allows scientists to calculate outcomes of experiments to an almost unimaginable level of precision. Technologies such as semiconductors, lasers, and modern electronics rely on these calculations and function exactly as expected. From a practical standpoint, the theory is not just successful, it is one of the most reliable frameworks ever developed in science. However, this success creates a paradox. While the equations produce correct answers, understanding what those equations actually mean in terms of physical reality is far from straightforward. In most areas of science, mathematics and intuition go hand in hand. For example, in classical mechanics, equations describing motion can be easily visualized. If an object moves with a certain velocity, one can picture its path. If a force is applied, one can imagine how it changes the motion. The mathematics reinforces a mental image that feels natural and intuitive. In quantum theory, this connection between equations and mental imagery begins to break down. The core mathematical object used to describe a system encodes probabilities rather than definite properties. It does not correspond to a clear picture of a particle moving along a path or existing at a fixed location. Instead, it represents a range of possible outcomes, each with a certain likelihood. Translating this abstract description into a concrete image becomes extremely difficult, if not impossible, using everyday intuition. One reason for this difficulty is that the mathematics operates in a highly abstract space. The quantities involved are not always directly observable and do not behave like familiar physical variables. They follow rules that are consistent and well-defined, but those rules do not align with the patterns our brains expect. As a result, even when the calculations are clear and logically consistent, the underlying meaning can feel obscure. It is as if the equations are speaking a language that is precise but not easily translatable into ordinary experience. Another challenge arises from the fact that different mathematical formulations can describe the same physical phenomena. These formulations may use different concepts or perspectives, yet they all lead to the same experimental predictions. This suggests that the mathematics captures something fundamental about reality, but it does not necessarily provide a single clear interpretation of what is happening. Instead, it leaves room for multiple ways of thinking about the same underlying processes, none of which can be definitively proven as the true picture. This gap between calculation and understanding often leads to a reliance on rules without deeper interpretation. Scientists learn how to apply the equations, how to set up problems, and how to extract results. The focus shifts toward using the theory effectively rather than fully explaining it. While this approach is practical and productive, it can feel unsatisfying from a conceptual standpoint. There is a sense that something important is missing, a clear explanation of what the mathematics is actually describing. The situation also highlights the limits of human cognition. Our brains evolved to interpret a world of solid objects and direct interactions, not abstract probability structures and non-intuitive relationships. When confronted with a framework that operates outside these familiar patterns, understanding becomes more about accepting the consistency of the mathematics than forming a complete mental picture. This does not make the theory less valid, but it does change the nature of what it means to understand it. In this context, understanding becomes layered. At one level, there is technical mastery, the ability to use the equations correctly and predict outcomes. At another level, there is conceptual clarity, the ability to explain what is happening in intuitive terms. Quantum theory excels at the first level while remaining deeply challenging at the second. This imbalance is what makes it both powerful and mysterious at the same time. The idea that particles can exist in multiple states simultaneously, often referred to as superposition, is one of the most striking and counterintuitive features of quantum theory. In everyday experience, objects are always in a single, well-defined state. A light switch is either on or off, a ball is either here or there, and a person is either sitting or standing. These mutually exclusive conditions form the basis of how we understand reality. The notion that something could exist in more than one of these states at the same time directly contradicts this deeply rooted way of thinking. At the microscopic level, however, systems are not limited to a single definite state before measurement. Instead, they are described as a combination of all the states they could possibly occupy. This does not mean that the system rapidly switches between states or that it secretly has a fixed state we simply do not know. Rather, all the possibilities coexist in a unified description. Each possible state contributes to the overall behavior of the system, and their combination determines the probabilities of different outcomes when a measurement is eventually made. This concept becomes clearer when considering how these combined states interact with each other. The different possibilities are not isolated. They can interfere in ways similar to overlapping waves. This interference can either enhance or reduce the likelihood of certain outcomes. As a result, the final probabilities are not just simple additions of independent possibilities, but the result of a complex interaction between them. This behavior has been confirmed through numerous experiments showing patterns that cannot be explained by assuming the system was in just one definite state all along. One of the reasons superposition is so difficult to grasp is that it resists visualization using familiar concepts. In classical thinking, combining states usually means having a mixture, like blending two colors to create a third. But superposition is not a mixture in that sense. It retains the distinct contributions of each possibility while still forming a single unified state. Trying to picture this using everyday analogies often leads to confusion because the underlying reality does not behave like anything in ordinary experience. The role of measurement adds another layer of complexity. When a measurement is made, the system no longer exhibits multiple possibilities. Instead, it yields a single definite result. This transition from a combination of states to one outcome is abrupt and cannot be described as a gradual process within the standard framework. Before measurement, the system embodies many potential realities. After measurement, only one is realized. The other possibilities do not appear in the observed result, even though they were part of the system's description beforehand. This raises important questions about what it means for those other possibilities to exist. Are they physically real in the same way as the observed outcome, or are they simply mathematical tools for calculating probabilities? Different interpretations offer different answers, but none has been universally accepted. What remains clear is that superposition is not just a theoretical idea. It has observable consequences that match experimental results with remarkable precision. Another important aspect is that superposition is not limited to a small set of states. In principle, a system can exist in a combination of infinitely many possibilities. This richness allows for a wide range of behaviors and is essential for explaining phenomena that cannot be accounted for by classical theories. It also plays a central role in emerging technologies that rely on quantum principles, where multiple states are used simultaneously to process information in ways that classical systems cannot replicate. The concept challenges the assumption that reality must always be definite and singular. It suggests that at a fundamental level, nature allows for a kind of coexistence that has no direct parallel in everyday life. This does not mean that the macroscopic world we experience is an illusion, but rather that it emerges from underlying principles that are far more complex and less intuitive than they appear on the surface.